you again. All right, so this is the problem. We're going to try to find the maximum positive moment that can be created at point D. So the first thing we need to do is draw the influence line. So to help you visualize that, I'm going to redraw this structure with my kind of virtual Mueller-Breslau release there. So that's where I'm going to take D. I'm going to take away its ability to withstand a moment, and then I'm going to see what the shape of my structure is going to, or how it's going to behave as I apply positive moments there. So if I now make a template and I say I want the moment at D, this is kind of what the shape should look like. So I'll go ahead and project down the position of the hinge and the support, and of course my point at D, and then the end of the beam, just to help me keep things straight. So what's going to happen to this point here at D? Is it going to move up or down? It's going to probably move up. So I'll just sketch in an up value. So that means from E to D, we'll get a slope like that. It's going to seesaw over C and do something like that. And then the hinge at B, we'll let it bend and reconnect at A. So there is the shape of my influence line at D. Now I just have to get some numbers attached to it. Now we talked about this a little bit before in class, but now we'll make it a little more formal. I think it's easier, if you're looking for the value at D, is to look at the case where the unit load is at D. That would be this point right here. So what that would be is a free body diagram that would look something like this. So let me, doing a lot of redrawing of the structure. So there's the geometry again. And now, since I want this value, I'm going to put my unit load at that point. And then what I'm going to come back and do is cut the structure there and try to find the moment at D for that load. So looking at the whole structure, it seems what I'm going to do is if I can find the reaction at E, then I can cut it, and then you can see the internal moment at D is going to be easy to find. It's just going to be the reaction at E times this distance. I'll go ahead and put those values back on there so you'll see them. So I am going to really be focused right now on finding the reaction at Y. Of course, there would be also a reaction at C and also one at A. See, I can't use this as my total free body. I have too many unknowns. So what I'm going to have to do is take it apart. This is going to be just a little bit of work. So if I take it apart at the hinge, I get a system that looks like this. So on the left free body, I will still have my reaction at A. I'm now going to generate a shear at B, equal and opposite on the other side, shear at B. And then there's my reaction CY, and then there's my reaction EY. And I'm looking for the situation where the load is above D, which is right here. So I'll go ahead and put the dimensions on there so you can see that. So I just took this free body diagram and I separated it right here at the hinge, and I created two.
You separated it because of the jump on the...
No, I separated because the hinge allows me to break it apart, and Now I have two free bodies and I only generated one new unknown. Okay, before, see, I had 1, 2, 3 unknowns, and really, I can't solve for that. Because my sum of x doesn't give me anything. So all I have is sum of the moments, sum of the forces. That's only two equations. I have 3 unknowns. By breaking it apart now here, you'll notice that this free body, I only have 2 unknowns. I can solve for that. And once I get the shear at B, I can pass it over here, and then I would only have 2 unknowns there. And what makes this easy, though, is look at this free body here. I'll call that free body 1. So this is now free body 2. So what's the shear at B in free body 1? It's 0. There's no load there. The load is where? Over here in free body 2. So there's no load. So the shear is 0. You could also find it by summing moments a day. If I sum moments a day, what does the shear have to be? 0. So if the shear is 0 here, that means the shear is 0 there. Equal and opposite. So now, all I want to find is the reaction at E. How do I find that? I will sum moments at C. So about C, the shear is 0. What kind of moment does my unit load make about C with right-hand rule? Negative. So it'll be -1 times a moment arm of 5 feet. And then my EY reaction creates positive moment. Forces EY. What's the moment arm? 15. So that says that EY is minus 1/3, right? No, it goes to the other side. It's positive, so it's just 1/3. Okay? So now I can come back and cut the structure at D. Look at the moment at D. And I have my reaction EY, which I just solved for, which was 1/3. So what's the moment here? Well, that's easy. I can just sum moments at the cut. Right? The internal moment is negative. The 1/3 creates positive moment with a moment arm of 10 feet. So it says the moment at D is 10/3 weird units feet. So that means that this value here is 10/3. And all these values will have the unit of feet. Now if it's 10/3 here, so the height 10/3 to this base, which is 5, what should this height be when it has a base of 5? It's the same. So it just becomes -10/3. And there's my influence line for moment. Now the problem asks, got to copy it down, but it wants to know what's the effect, what's the maximum positive moment at D for a concentrated live load, a uniform live load, and a uniform dead load. So let's do the concentrated force first. You can't see it, but in the problem statement, that value was 4 kips. So where should I put my 4 kips to create the maximum positive moment? I should apply it at the maximum positive value of the curve, which is right here, which is right over D. And it will be 10/3. So the moment at D, for this part, will be the load, which is 4 kips, times the maximum value, which is 10/3 feet. That's 40 divided by 3, so that's 13 0.33 kip feet. So that will be the moment produced at D for a 4 kip live load moving across the structure. And actually its position will be right at D. Okay? So that's the first one we need to consider. The second one we consider will be a dead uniform load. We've done one of these in the past. The value for this problem is 200 pounds per foot. I'll do it in kips, so that'll be 0.2 kips per foot. Now remember, the moment at D due to that load is what? You take the intensity of the loading times the total area under the curve. Okay? So the intensity of the loading is 0.2 kips per foot. And now I'm going to multiply it by the total area of the curve. They're both triangles, so it'll be 1/2. And then I'll handle each one separately. So this triangle is 1/2 base times height. The base is 10 feet. And the height is minus 10 over 3 feet. That takes care of this part. The positive part has a bottom dimension or base of 15 feet and a height of positive 10 over 3 feet. So what's that equal to? It's like 50 thirds, 25 thirds. I don't know. 1.67 kip feet, I'm guessing. You guys have to get out your calculators. Or someone will. It should be positive because this term is bigger than this term. What did you say that again? I guess 1.67. Is that right? I'm a good guesser. Except when it comes to the lottery numbers. I'm terrible at that. I've yet to get that one right. Anybody win anything from the lottery yet?
$4.
Good for you. You know what I did win one time? Another ticket. I tell you one thing, it's a long line at my Kroger to get to that machine that dispenses lottery tickets. So I guess people, after they buy their groceries, feel like they have to go try to win some back. I don't know. I've seen guys just shove $20 bills in that thing for like a minute, like it's a slot machine. Terrible. Okay, now this is the new part that we haven't dealt with before. This was a dead uniform load. Now we're going to introduce a live uniform load. Now what's different about a live uniform load is that even though it's uniform, it kind of can move around. Okay? And we're only going to position this load over the section of the beam where the influence line is positive. Okay? So my live uniform load was 300 pounds per foot, so that'll have an intensity of 0.3 kips per foot. So when I'm looking at I'll go ahead and put this here. I'm just looking for the positive moment. So I'm still going to have my intensity, 0.3 kips per foot. It's still going to be triangular areas. There's my 1/2. But now, unlike a dead load that extends over the whole structure, so you might have negative, you might have positive areas, with live, you put it wherever you want. So where do I put it to create the maximum positive moment? Just over the positive sections. Okay? So in this case, just the positive area is between C and E, so that would have a base of 15 and a height of 10 thirds. Pretty cool, huh? So that should be 7.5?
Yep.
So the total would be the sum of all those. So these two together are 15 plus that looks like 22.5 kip feet would be the maximum positive moment at D. Now I've run out of space, but I'll try to squeeze this in. So what would all this loading look like on the beam? So I'll just kind of make a little quick sketch. Of the structure here. So there's my simple support. There's the pin. There's the pin. So first, the dead load. You might remember the dead load. I'll underline that in blue. The dead load goes over the whole structure. You can imagine the uniform load over the whole structure. This live load, I'll do it kind of in this orange color. We're only doing that over the section C to E, which would be from here to here. See that? And then the concentrated live force, I'll do that in like purple, that's applied right at D, which is here. So that's kind of a load combination, concentrated load, live load, dead load, that would produce the maximum moment. So this is the live load, this is the dead load. What if I wanted the maximum negative moment? What would change? Well, I wouldn't put my concentrated load here. Where would I put it? Put it here. That would create a negative value, right? It'd be right over the pin. Does the dead load value change at all? No. Does the live load value change? Yes, it would only go from A to C. And we have to look at numerically if all that actually produced a negative value. It may not. Because, see, our dead load came out positive. So that kind of combines everything we've been learning about influence lines for a couple days. We're drawing a pretty sophisticated influence line and then using it to solve a problem with combinations of live and dead load, both concentrated and uniformly distributed. Any questions about that?
Can you explain the live load one more time? How you came to 22.5?
Well, the live load can start and stop wherever you want it to. So you start and stop it where you create the maximum positive value. So you wouldn't have it at all over the negative part, just the positive part. So for us, that starts on this problem from C and goes to E. So I just want the area of this part of the curve. So that's how I got the 1/2 base 15 times height. And that's why I kind of drew it like this. So you see it only extends from C to E. The dead load, you don't get a choice. It's the whole distance. But that was for positive, right? So if we want to do negative, this live load would shift and go over from A to C only. Because it would cover up or extend over just the negative portions of the graph. We'll do some more of those. Hopefully that'll help clear it up.